Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for Calc 2 or differential equations students who are going through and doing power series, and you possibly need to take the product of a couple power series. And when you do so, you need to understand very early on in your mathematical career that you're not going to multiply everything out. You're honestly going to be asked for maybe the first 2 or 3 or 4 terms of the expansion. Any more than that would be ridiculous. So again, the skill is going to be useful in differential equations, and you learn it in very simply in Calc 2. Actually, I say very simply, but the skill is the same whether you're in differential equations or you're learning it for the first time in Calc 2. Same exact moves. So first thing you need to understand is you are required to remember the power series expansions, or the Taylor series or Maclaurin series for e to the x and cosine of x. In this case, I'll just go ahead and write both of them out. All right, there we have it, e to the x and cosine of x. Now, of course, we weren't dealt e to the x here. We're given e to the negative x squared, but I wanted to at least showcase the Maclaurin series for e to the x and cosine of x. But now that we know it's e to the, negative x squared, I'll trade that out and I'll clean up that power series right there. There we go, done with that. Now we need to take the product of these two series. And if you think you can just multiply everything out easily, no, you cannot. Let's go ahead and take an example off to the side as to showcase why you cannot just do that. Let's pretend as though you have a simple series x to the nth, where n goes from 0 to infinity. And let's say you want to multiply that against, let's say just a completely different series, n equals 0 to infinity of y to the nth. And actually, to make this argument a little cleaner, let's actually just do it from n equals 0 to 1. This will very much showcase what I want to showcase, even if we only go to the very first term in both series. Now, I want to convince you that this is not the same as the summation n equals 0 to 1 of x to the nth times y to the nth. Why am I saying that? Well, because if you were to expand this red ink, this would be x to the first, actually 0th, times y to the 0th, plus x to the first times y to the first, or in other words, 1 plus xy. However, if you were to actually look at the problem handed to us, it is written, if you expand these out, as follows. The first power series is going to be x to the 0th plus x to the first, and we're going to multiply that by the second series expansion, which is y to the 0th plus y to the first. That's just going to be 1 plus x times 1 plus y. And if you were to multiply that out, you get 1 plus, let's see, I'm just going to do it this way, 1 and then y plus xy. I hope you would agree that is completely different than this statement right here. These are not the same statements. So this should be a decent justification as to why a product of power series is not the same as the power series of the product. Kind of weird to say that, but there you go. So what does this mean in the case that we're considering right here when we take the power series of e to the negative x squared and multiply it by the power series of cosine of x? Well, that means that you have to do term by term multiplication. In other words, you need to expand out both of these series for a little bit and then multiply terms against each other. Now, that is going to take an infinite amount of time. Let me showcase this with some clean handwriting. There we go, e to the negative x squared times cosine of x. We have them there. They're the same as our power series up above. And let's go ahead and expand out each of those power series just a little bit. You don't need a ton of terms. Let's just expand out a few terms. Notice I went ahead and expanded both of those out until I got to the 6th power. I didn't really need that much, but I just wanted to showcase that. Now, if you were to try to multiply this out through the distribution process, you would be sitting here literally forever and ever and ever. But luckily, the instructions ask us to find the first 3 non-zero terms in the Maclaurin series for that function. In other words, I just want to find out what is the constant term, what is the x to the first, what is x to the second. And if that doesn't give me 3 non-zero terms, I'll go a little bit further. So let's go ahead and take a look here. The constant 1 times anything in this group of numbers over here. Well, the reality is the only number that I can multiply by to still get a constant is this 1. So 1 times 1, get a beautiful 1. Now let's go ahead and look through. Is there any way you can multiply things to get a power of x to the first? And the answer to that is no. So now I look through and say, how can I get an x to the second? Well, 1 times this term right here and negative x squared times this 1 here. Those would be the only terms that would multiply to give me an x squared. So let's go ahead and write that in. I'll use a different ink for this. So there are 2 terms. I know you think there are 3, but actually those 2 terms in green, I'm going to factor the x squared out of. And so it'll be a 1 plus some constant times x squared. Now we need to check to see if we have an x to the third. Well, if you look through this, you'll see you're only multiplying even powers of x. So you'll never get an x to the third. So let's move to the x to the fourth. Take this 1 from this group, and I know I can multiply it against that x to the fourth right there. In fact, I'll go ahead and write the result right now. The next thing I'm going to do is look at this x squared term. What can I multiply it by in the second group there that will give me an x to the fourth? And if you say this x squared term, you're absolutely correct. And finally, this x to the fourth term right here, I'll multiply against that 1 to give me the final x to the fourth term. And I'll note to the reader that this summation continues forever. These would not be equal if I stopped it right there and didn't write plus ... I'm writing plus the ellipses there to indicate to the reader that if I had all of eternity to write this out, I would go ahead and do it. But I don't have the time. So let's go ahead and clean this up. This is going to equal 1. And then I'll factor off an x squared out of this group. You can double check my mathematics, but that actually does work, and I'll clean up the coefficient in a second. Let's go ahead and factor an x to the fourth off of this group. All right, so far so good. We have somewhat of an expansion going on for this product of functions all the way at the top. Now let's go ahead and do our last final cleanup. That's just a 1/2 plus 1. That's going to be a 3/2 right there. And over here, I have a 1/2 plus a 1/2, which will be a 1, plus 1 over 24. So 24 over 24 plus 1 over 24 is a 25/24. And we have x to the fourth. And I wrote approximately there because now I am just stopping. I'm truncating the actual addition to that. So this is a 4th degree Taylor expansion, or really in this case, because we're centered at 0, you can call it a Taylor expansion about 0, 4th degree Taylor expansion about 0, or you could say it's the 4th degree Maclaurin expansion. So either or, it doesn't really matter to me. It's the 4th degree polynomial expansion of that product of functions all the way at the top. So this is a decent approximation, not the best, but a decent approximation of y equals e to the negative x squared times cosine of x, at least about the center, x equals 0. And to drive this point home, let's go ahead and graph that function, the product of e to the negative x squared times in the cosine of x. We'll graph that first. So let me go ahead and type that in. Kind of a beautiful function. If I zoom in there, you can see this. Let me put this on a better mode. Some people really like a different kind of a dark contrast here because it's easier on their eyes. So this is the function e to the negative x squared cosine of x. And remember, our Maclaurin series expansion, which we only did a 4th degree Maclaurin series expansion, was centered at 0. Let's see how accurate that is. So far, I only wrote the first term, y equals 1. Now we're going to write the second term. And you can see right now, already with only 2 terms to the expansion, we have a really good approximation of this function centered around 0. It's really good until you get to maybe negative 0.3 and positive 0.3 roughly. Very good approximation in that region. But let's make it even better with our third term of the expansion. There we go. 3 terms to the expansion, and notice it locks in pretty nicely all the way out to maybe a negative half and a positive half. So again, I can use this polynomial to approximate e to the negative x squared cosine of x in a short or a very narrow neighborhood about 0. In fact, let me go ahead and name these functions. So f of x will be the original function, g of x will be our polynomial approximation, and if I want to know what f is at, let's say 0.2. Well, we see the function, the original function's about 0.9416376, somewhere in there. If I look at g evaluated at 0.2, you can see pretty decent approximation. I get 4 digits of accuracy already. Well, technically 3 when you round, but there you go. So that's pretty darned good. Remember, the further away you get from that center, the worse the approximation will be. And you can see they start losing accuracy as you move away from the center. You gain accuracy as you move toward the center. That is actually a pretty great demonstration of how accurate our polynomial is as you get toward the center. All right, I hope this video was helpful. Again, it's very useful for both differential equations and Calc 2. All right, you have a wonderful day. Hope to see you in another video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.